class. Okay. And yeah, so after processing your data, you get an output, which is going to be different depending on the type of task you're looking at. If you're looking at something at the node level, you're going to want a node embedding. And this type of situation will be, for example, classification or regression at the node level. At the graph level, you're going to be looking at a graph embedding, so generally aggregating the node embedding from all the nodes in your graph into a single representation, similarly to average pooling for an image over all the pixels. And finally, one thing I haven't talked much about is edge embedding, so edge level prediction. And this is the situation where, as I mentioned earlier, you can have also edge features. And in this situation, you could be wanted to be predicting some kind of existence of a link between two nodes, or just type of edge that exists between two nodes. So the node and graph embeddings are two types of problems that I find a bit more easier. So in this tutorial, well, in this tutorial, we're going to be looking at the PyTorch Geometric framework and how we can use that to implement a graph neural network. We're going to implement two simple graph and node classification models, and we'll be going to be implemented and using graph convolution operators. So unless there are any questions now, I could move on to the notebook. Is there any question? No. Okay. Okay, then. So let's move on to the notebook. So is everyone doing okay with the notebook? Any issues? I'll take that as a no. Okay, so let's move on to our first step is going to be building a graph using the PyTorch geometric format. So a quick recap of what the graph is with a slightly more mathematical point of view. So your graph is a set of nodes and edges, as I mentioned, and the edges describe the relationship between the nodes. Your graph can be associated with a feature representation. And we also have a way of representing the graph connectivity using a matrix, which we call an adjacency matrix. So this is a square matrix that is going to describe whether there exists a link between two nodes. So entry aij of the matrix is going to be positive if there exists a link between node I and j. So your matrix can be binary, which means zeros and ones. And this just means there exists a link. You can also have a weighted graph, which is situations where your matrix is populated with continuous values. So you have zero, no edge, or just a continuous value existence of an edge with the weight that corresponds to the value of your aij entry. Something to note as well is the distinction between directed and undirected graphs. So undirected graphs just have a connections between two nodes. So for example, in the Facebook network, it's going to be existence of a friendship link. A directed graph is going to have as the name suggests, a direction from one node to the next. So you could consider, for example, on a Twitter graph, the relationship will be node 4 is following node 1. And this is generally a little bit more complicated to process. Most of the methods that have been developed have been focusing on undirected graphs. So it's good to know that directed graph exists, and it is generally a bit more challenging to deal with them. One of the reasons is because your adjacency matrix is going to be symmetric only if you have a directed graph, which makes things a lot easier in general. So how do we implement a graph object? So we're going to use the PyTorch geometric graph object, and it's a very, very simple thing. We just have to use the data class, which is going to encode, all the key properties of your graph, which are the node features, the node position in space, the edges, and their attributes. And they're all encoded with very specific variables. So to define our graph, we're going to first describe our node features, describe node positions in 2D space. We're going to define a set of edges. So this set of edges is a tensor that describes the starting node and the destination node. So for example, if you have 0, 1, and 1, 0, it means your edge is undirected, or that it's symmetric. In our setting, as you can see, we have a directed graph because we don't have symmetric connections. We can also add self-loop, which is a collection from a node to itself. And then we also have a set of labels if we're going to be doing, for example, classification on our graph nodes. Now, to create our graph structure, it's actually very simple. We just need to call the data object and populate all, sorry, there's a thing, populate all our variables using the ones we just defined. And that's it. We have created a graph. So as you can see, it's very easy to create a graph using PyTorch Geometric. And we can also visualize this graph to make sure we have created the graph we were looking for. So to do that, we can use the relationship between PyTorch Geometric and NetworkX. So NetworkX is another very good package for graph processing in Python. You can use it for pretty much everything that's not deep learning or PyTorch related. So PyTorch Geometric has a very nice series of util functions to convert your graph to a NetworkX graph. So as you can see, it's just calling the toNetworkX function. And here we just input the data. You can also decide if you want to convert your graph to undirected or not. In this specific situation, we're going to say false and look at how to create an undirected graph using the PyTorch Geometric pipeline. And then we can just call nxDraw and draw a graph. So this is all the command you need. Now, to make it a bit prettier, we can also add additional information, such as the position of the nodes. And we can also add label information because we know the label. So we're just going to add some kind of coloring to make our plots a little bit prettier. But all you need is to call nxDraw of the graph. And this is the color map, and we're just going to add color that corresponds to the labels. And this is just for subplotting. Another thing we can do is visualize our adjacency matrix, which is based on the edge. And we can do that using another nice util function from PyTorch Geometric, which is called toDense edge. And this is going to convert your edge, your edges into a square adjacency matrix. And you can also plot that using imshow. So let's have a look at this. Sorry. I swear it works. Okay, so this is our graph. As you can see, we have a directed graph. Those edges are all directed, and this is our adjacency matrix. And because our graph is directed, the adjacency matrix is not symmetric. Now we want to look. We can also have a look at what the graph looks like if we convert our edges to undirected edges. So again, we have a very nice PyTorch geometric function which allows to do that. And you've guessed it, it's another util function. we simply call toUndirected on our edges. And we can create a new data object using the same data, but the undirected edge. And then we can just plot the same thing. But replace with our undirected graph, and we should be getting an undirected And there we go. So visually here, the difference is subtle. You can see that there's just arrow pointers in both directions, which shows that your graph is undirected. More interestingly, you can see that now the adjacency matrix is symmetric. And this will be the key difference between directed and undirected graph structures when trying to process the data. Okay, so also feel free to interrupt me if you have questions. Now that we've built a graph object, we're going to be looking at building an actual graph classifier. So now we're going to be looking at an actual real data set, which is a protein data set. It's a data set that aims to classify proteins into whether they're enzymes or not enzymes. And again, PyTorch Geometric has a set of data sets that are already pre-processed and available to download. So it's quite convenient to use standard data sets. All we need to do is import the right data sets, specify where we want to download the data and which data we want to download.
Sarah, there is one question in the chat and someone raised their hand. So in the chat, Ankit asks, can we use spectrum methods on directed graphs?
That is a good question. I haven't seen spectral methods being applied on directed graphs. I think generally people are converting their directed graphs into undirected graphs. I would say spectral methods might not be the best solution for directed graphs. There are methods which are more specific to like directed graph structure, what your edges might mean, other that are more looking at aggregating information in the neighborhood where there you can mainly look at incoming messages. So I would say if your graph is directed, maybe use something different.
Thanks.
Okay, and I think it was, now his hand is not raised anymore. I think it was Hatish who had
Hi.
hand raised.
So my question is like,
yeah.
so each node is represented as a vector, or how is it? And the connection between two nodes is also a vector. How is it represented mathematically?
Well, no, yeah, in practice, each node is just a vector. So, for example, here, this is just what you need to define your nodes. Why is this moving? You just have a set of vectors that describe each of the nodes. So think of it as you have a data set and you're trying to process each of your samples individually, like what you would do with an MLP. Now, the difference between this and using a graph is that you're going to also take into account relationship between these samples. I don't know if that clarifies it.
Yeah, thank you.
Okay. So we have downloaded our protein dataset. Just a couple of different statistics about the dataset. We have about 1,000 graphs. Each node in the graph has 3 features, and we have 2 classes. So it's a binary classification problem. So here we don't have an official split on training and testing data. So we're just going to randomly shuffle the data set and select a subset for training and a subset for testing. We can also have a look at our graphs in the data set. So if you select an example from your data set, that's going to give you another data object, which is the same thing as the one we just constructed. And again, you can print the number of nodes, the number of edges, the number of self-loop, and whether the graph is undirected. And you can also visualize it using NetworkX. And these are graphs. So in this data set, your graphs are going to have different size, so different numbers of edges and different structures. So question, why is directed graph difficult to model over undirected graph? Yes, it's because of the symmetric matrix. We make a lot of assumption processing the data that the matrix is symmetric, and it's very convenient, especially for spectral methods where we're going to be doing some kind of Fourier transforms and eigenvector decompositions. As soon as your matrix is not symmetric, it gets a lot more challenging. You can also look at a different example if you want and see that the graphs look quite different. So, you know, very different from the one we just saw, a lot less nodes and edges. So quite a diversified data set. And before you can actually build our model, we are going to be looking at the data loader classes. And it's another difficulty that we have with graphs. It's that to build a data loader, to build a batch of graphs, we can't really directly stack our graphs because they all have different sizes. So you need to find a different way to create a batch of data that we can process together. So what PyTorch Geometric has done is to build a diagonal block matrix of adjacency matrices. So what it means is that you will have a series of matrices which each are going to be the adjacency matrix of your different graphs. And you're going to concatenate them in a way that there are no connections between the different graphs. So you will have a very large graphs, but it's going to be made of a set of small graphs that are not connected. For the feature vector, we can simply concatenate them, and for the labels, the same thing. So thanks to this, we're able to process everything together as a big adjacency matrix where our small graphs are not connected. And in terms of coding, it's very, very simple. It's pretty much the same interface as standard PyTorch. You just call the data loader class, input your data set, your batch size, and whether you want to shuffle. And that gives you a batch. And again, you can look at whether the batch gives you some graphs and you get access to the data again. So we can move on to the fun part now, which is going to be building our own graph convolution operator. So are there any questions that you say? Oh, there are questions. Sorry. How is scaling done? So you can look at normalizing the features. So one thing that I haven't mentioned actually is the dataset class. So here, when you download your dataset, you can also add some kind of transform. So like in your general PyTorch, you can apply transformations to your image. So PyTorch Geometric also has implemented a set of transformation functions, which you can apply to your data during the data loading part.
Just a follow-up question. So is it applied to like particular node, like the feature of node, and like scaling all the nodes?
Yeah, generally you can do like normalization of the node features.
And like for me, the use case would be like, suppose meshes. So how would I think of applying normalizations on mesh like, or manifolds, geometric manifolds?
So if you have a mesh, I think it's a bit different, because generally the information you have on your mesh might be just the coordinates.
Yeah.
So I think in this setting, you might want to approach it a bit differently. I mean, you might want to normalize your coordinates so that they're all kind of coherent across different types of structures. But I don't think you need to process coordinate as much as you would with like features, node features. So I think it's a little different there. Full disclosure, I haven't done a lot of work on like mesh processing. It's mainly been processing features on a graph.
Okay, thanks.
What is the feature of graph in general? Sorry, could you expand on that question? Not sure what it means. What is the feature of graph in general?
I think maybe it means the node features, maybe, or
the node features. So it would be anything you would want to describe what your node represents. So for example, in this protein data set, actually don't know what node features are in this protein data set. That's it. But for example, let me think of an example. Okay, let's say you're looking at images and your graph is going to be this regular pixel structure. So the features on your image are going to be the image intensity. Does that clarify it? Take that as a yes. Thank you. Okay. Okay, Robert asks, with the same example ID, why does the resulting visual look different every time I execute it? That is because I think NetworkX is I think the default plotting of NetworkX is random plotting. So you will have different types of representations in space. If you're talking about the batch here, it's because you're going to be randomly shuffling your data. So it's going to be looking different every time. I don't know if that's what you mean. Can you not use ANNs where the connection between nodes is encoded as a feature for each node? I mean, I think encoding the information, the relationship between other nodes as a feature for each node is actually what graph neural networks are doing. So you're going to basically update your node features based on, okay, I can share the link again. That I can do easily. Okay, so yeah, to go back to that question on using regular neural networks and encoding relationship information in the node itself, that's pretty much what you're doing with graph neural networks. You're going to be transferring information from your neighbors, information of these relationships to your node. So I don't really know how you would do that in a different way. But that's pretty much what you're doing when using these graph structures. And if you don't use information on the relationships, generally you get a lot worse results because you don't have this kind of neighborhood information that is really useful to learn better quality features. Okay, let's proceed. So we have loaded our data, downloaded our data, built our data loader, and we are ready to throw this data at a neural network. So now we're moving on to the fun part, which is building graph convolutions. So as I mentioned, we're trying to reproduce what we do with images, which is like learning high quality representation of our input data by exploiting the underlying structure and neighborhood information. Now, because our graph structure is a bit irregular and there's no nice neighborhood consistency across nodes, there's a lot of different ways we can process this. And a very nice way of representing the different convolution operations is to use something called message passing. So this is what PyTorch Geometric is relying on to code the different convolutions. And it's quite useful to understand what's going on exactly in these different convolution methods. So what happens is first we compute a message for each node, depending on its neighborhood and its edge information. And the message is going to be computed according to a function phi. Afterwards, we're going to aggregate information from the messages to a given node according to its neighborhood. So these nodes are going to be computing a message. Then we're going to aggregate information according to a specific function, which is this square function here. And once we have propagated all the information, all the messages across the graph, we are going to update our node representation using another function, gamma. So it's a bit difficult to grasp sometimes, but basically you're going to compute a representation of your node, which is going to be propagated across the graph. And for each node, you're going to aggregate information from all its neighbors, so aggregate messages from all its neighbors to compute a new representation of your node. And the different methods are going to differ based on how the neighborhood system is defined, how we propagate information, and the different ways we define these functions. So the message passing class is going to basically implement these different functions. So we have the message, aggregate, update, and propagate functions that we need to fill to describe exactly how we're going to be doing the convolutions. So the names are quite self-explanatory. Message is going to be computing the message, so implementing the function phi. Aggregate is going to specify how we are going to aggregate the messages of a node and its neighborhood. So here we only have three options that are implemented, which are the add, which is just going to be adding the messages in the neighborhood, min, and max. If the neighbors have incomplete information. So if your graph nodes have incomplete information, I don't think there is a common rule on how to deal with that. You can pad it with zeros. You can add like mean values of the features. You can also choose to ignore some of it. It's basically, I think, something you have to try and test yourself. You can also try to learn to impute the missing data as well. So yeah, it's always a bit challenging when you have missing data and there's no gold standard way of dealing with this. Thanks. Yes, and the update function implements how you finally update your feature representation using this gamma function. And finally, the key function is the propagate function, which is going to be propagating the messages across the graph and is going to be calling internally the three message, aggregate, and update functions. So as an exercise, we're going to implement a gene convolution operator, which is a somewhat recent method from 2019, I clear. And gene is defined by this following update function. So we can relate this update function to the message passing formula, which is used to implement our graph convolutions. So based on this, we can look at, sorry, there's the questions. X are the features linked to the node of the graph, while Ni encode the topology of the graph. Yes, that is correct. So X are the features, and Ni, so if you look at, let's say, look at this node, the neighborhood is going to be looking at which nodes it is connected to. So the methods have different ways actually of defining neighborhoods. Most of them are just looking at the direct connections. But you can also look at, for example, second order neighborhoods if you want to do something a bit more looking at larger neighborhoods. I don't think there are additional technicalities to message passing when you have self loops. Oh, you mean when the graph has loops? No, I don't think there is anything particular to deal with.
There is no problem with respect to convergence of the updates, in a sense, like at which time you should stop, like does this update should be some form of a fixed point equation, these kind of things. At least it's like in inference, for example, there are message passing algorithm, and typically when the graph contains loop, it's like not clear whether or not like the algorithm is going to terminate at some point, whether or not it's going to converge and everything. It's a bit different in that case.
Yeah, no, I don't think you have this problem there. I can't tell you exactly what happens because I don't personally remember what happens exactly in the message passing process, but I've definitely used graphs with loops and it's been fine. This approach should work with directed graphs, yes. It should work because of the neighborhood system. So if you like define how you aggregate your neighborhood system based on the incoming connections, then you should be able to use directed graphs, yes. The reason why it's a bit challenging in other types of methods is because they were not necessarily designed according to this specific formula. So some of them are absolutely relying on the symmetry of the adjacency matrix, which will make it more complicated for directed graphs. If the features are incomplete, how do we make sure that we are not aggregating different features? So that is up, I would say it's up to you to kind of also clean up your data a little bit. It's the same way that if you input to a CNN an image that's incomplete, you're going to struggle to learn high quality features. So you could consider, for example, masking some of the nodes that are unreliable if you feel like it might hurt your propagation process. Can we learn the optimal function? I guess you could. I mean, I guess there could be ways of doing that with, like, for example, gating and trying to find the right function. I don't think it would be straightforward. It's always a matter of like having too many moving components, and then it might be difficult to actually learn or converge to anything. Okay, so let's implement our gene convolution. The first thing is the message, which is just, if you look at this formula, this function here is just the node feature itself. So our message is very, very simple. We are going to return the same node value. Second, our aggregation function here is a sum. So we're going to look at the aggregation function and specify that it's the add function here. Oh, hot group permutation invariant, rotation invariant, and more. So this is a lot of specificity to the different methods that exist. This is accurate. Oh, someone else probably did better answer than me. I think all of the convolution methods are looking to create permutation invariant, rotation invariant. Because you're looking at a node level and its neighborhoods, it's generally quite easy to have this kind of invariance. It can be a little not straightforward at times. With spectral methods, you don't necessarily have all these invariances that. Okay, sorry, let's proceed with the tutorial. Okay, let's go with the updates then. So our update function is a little bit more complicated. As you can see, you have an epsilon variable, which is going to be a learnable variable, and an h function, which is going to be an arbitrary neural network. So we need to define two components to this neural network, which is going to be the h function, which we're going to put as an input. So we have flexibility in terms of how we want to process our features. And we're also going to be defining our epsilon variable, which is going to be a learnable parameters that is initialized by the epsilon variable we put as input. Then to do our update, so this is our node features, and this is the output of our aggregation process after propagation. So this is going to be this aggregation. So what we do is we are going to update our feature representation using our epsilon variable. And add the output of our aggregation process. And finally, we are going to return the transformed features. And the last step is defining the forward operation. The first thing we want to do is remove all self-loop to make sure that we don't aggregate information in an inaccurate manner, because we are going to be adding node information in this step. So we don't want to have the self-loops here. And finally, all we need to do is call the propagate function. Which takes into account the edge index, so the connectivity of the graph and the feature vectors. And that's it. We have implemented our chain convolution operators. So if you want to implement different convolution operators, generally all you need to do is change this message update and forward functions a little bit. So we can test it, verify that it's not buggy. Let's get some data from our data loader. We can define our MLP as a sequence of linear layers. So this is going to be the dimensionality of your convolutional operator. And let's add another one. And you can define your convolution using the function we just defined, which takes as input the MLP network and compute our features. So the convolution takes as input the feature representation of your nodes and the edge, the connectivity of the graph. And hopefully this should work. Sorry. And there we go. We have implemented a convolution operator. I think that's pretty cool. And it's pretty nice that we can do that so easily with only a few lines of code. So before we run out of time, let's train an actual convolutional neural network. So here I have predefined an MLP class to make it a bit easier. And we're going to define a model that has 3 convolution layers and the classification layers. So it's quite easy. We're going to be creating a bunch of gene convolutions because we just created it, so why not? And yeah, sorry, slow. And finally, add our classifier, which is going to be a linear layer. So the forward process is pretty much very similar to what you would get with a regular convolutional network. You're going to apply your convolution operator to your nodes. We can add some activation function. Repeat the process with our other 3 layers, 2 layers, 2, 3. We can add some dropout to our node features. It should be constrained. This is correct. One thing is the pooling layer. So as you know, because we're doing this kind of batching with block matrices, it's not that straightforward to do pooling layers. So fortunately, PyTorch Geometric also has implemented some so-called readout layers, which are going to be doing the pooling for you at the matrix level. So we don't necessarily need dropout. I find that these models, these graph convolution models, tend to overfit a bit more than regular data. So I played with this model a little bit ahead of the tutorial, and with dropout, it works a little bit better. But yeah, it generally depends on your data. It's not always necessary. And lastly, we add the weight function, the classification function, and we return X. So we can build a model, which is going to set to take, okay, come there, not features. Let's use 32 as our dimensionality, and our output is going to be dataset num classes. Now, because here we're doing binary classification, we're just going to have one output, and we can create our model architecture. And GenConv is not defined. Sorry for the typos. Okay, we have a nice model architecture. So now let's train a model. So this is a very standard set of training functions. We define our optimizer, our criterion, which is a binary cross entropy with logits. Our train function is going to be looping through the data loader. So this is going to be one whole epoch. Compute a forward function, compute the loss, backward in step. And our eval function is going to be going through data loader again. So let's train this model and see what happens. Hopefully nothing breaks. Okay, there we go. We have our loss function going down, or test accuracy going down, train accuracy going up. So while it rains, let's see, we have a new question. The classification layers at the end of the network, how do you think of it with GNN? So when you're working with at the graph level, because you're going to aggregate all your information from all the nodes individually, you do need some kind of MLP to kind of process your nodes in the end to get to classification. I guess you could also skip the classification layers, but I find when you aggregate information from all the graph, I find it to be more useful. If you're looking at the node level where you're going to process your data, you don't necessarily need a classification layer. In fact, in the last section of this tutorial, which is node classification, which I'm not sure we'll be able to get to, but I hope we do, there's no classification layer. So actually you do need one here because you're going to aggregate information from the graph as a whole. So yeah, as you can see, our gene convolutions are a bit unpredictable at times. So in the paper actually that proposed these methods, they also processed the protein data sets, and they added a lot of different tricks to make it work a bit better. So they added some batch normalization, they have more layers. So here, don't expect amazing performance. Is the crowd net processing one node at a time? No, it's not. It's not. The formula is just kind of way to define your update function, but everything is processed together, and the propagation operation processes everything together. Okay.
So Sarah, because we only have 2 minutes left, perhaps we could leave it here and share the notebook with the field
yes,
remaining
sure.
parts node classification.
Happy to. So it's pretty much the same thing, honestly. Just an idea of what you can do. Instead of doing graph level classification, you can do node level classification. And the key difference is going to be in the data loading part. So you don't have to create a data loader, you just input your whole graph, and it's more of a semi-supervised setting because you will have part of the graph that will be masked, part that will be labeled. And yeah, definitely share the rest of the tutorial, and there will be explanations of the different steps. So you'll be able to play with this last section of the notebook. Yes, I will share a completely filled version of the notebook at the end, so you can have all the information.
Yes, so we can send that maybe if you have it here, like now in the chat, or you can send it and I can send an email.
Yeah, I think maybe it's better to send an email so that it's not lost in the chat.
Okay, yes, no problem. So I'll send an email afterwards.
Yes.
Complete notebook.
In terms of the question of how much better it is to use a GNN compared to using node features only, there is actually a comparison at the end of this tutorial. So we have a comparison between a GNN and a, I can actually show you the field version. Give me 1 second. So there's a comparison between features using GNNs and features using an MLP only, and you can see quite a big difference in terms of the performance you get. So let me see if I can find the field version. Okay, I have it. Spoiler. Okay, so this is a node classification model that you have trained using GCN, so using pairwise relationships. This learns this set of features, which is not perfect yet because I don't think the model is fully trained at the time. But you have this nice, somewhat separation of the different types of feature. So it's kind of a clustering of the feature representation in 2D space, and the colors correspond to the feature, to the node class. So it's good if we have nice clustering of the different classes based on their, of the different nodes based on their class. Now, I did the exact same thing with an MLP, so something that just doesn't take into account pairwise relationship between the nodes. And in this setting, you have a feature representation that is much worse, and overall performance that is much worse. So you will be able to play with this when I share the final notebook with you.